Hi, class. So this week we're going to talk about free fall. So this is again motion in one dimension and free fall. So free fall simply means an object that is freely falling. Okay. So what is free fall? An object is in free fall if it is being acted upon only by the force of gravity. Okay. So basically anything that would um, a rocket, for example, that is being pushed upward with an engine would not be in free fall because it's not just being acted upon by gravity. An airplane that is being affected by um, by the engines and the wings would not be in free fall because it is not only the only force acting on it is not the force of gravity. Someone who's parachuting down to the earth and is and floating down to the earth, but this parachute is kind of helping them fall gradually and slowly, would not be in free fall because they're not just being acted upon by the force of gravity, they would also being acted upon by this upward force of the parachute pushing against the air. So basically, free fall is just an object that's freely falling through the air. If we throw a baseball up in the air, we would say it's in free fall. If we drop a rock off a bridge, we would consider that to be in free fall. If we drop a feather, we would not consider that to be in free fall simply because even though gravity is pulling it down, a feather is so light that the air that it's falling through um, affects how it moves. So we would say that a feather has a lot of force due to air resistance acting on it. So we would say a feather falling through the air on Earth would not be considered free fall. But if we took the air away, a feather falling, let's say, on the surface of the moon, that would be considered to be in free fall because there would not be any air resistance. Right? So basically, it's got to be an object that it's effectively only being acted upon by gravity. So even though a rock, you could argue when you drop a rock, it is being affected a tiny, tiny, tiny bit by the air. We say that the amount that is affected by the air is so negligible that we can consider the rock to be in free fall. When you drop a feather through the air, the amount that the feather is affected by the air is significant. So we would say it is not in free fall. So when we drop most objects, when you drop a set of keys, when you drop a rock, when you drop a baseball, when you throw a apple up into the air, we would say that those objects are in free fall. Okay. Um, so again, technically an object would have to be in a vacuum to achieve free fall, but we're going to say anything where the effect of air is really, really small is going to be considered to be in free fall. Okay. So we will effectively ignore the effects of drag, and drag is air resistance. And we're going to assume objects that have very, very little drag are freely falling objects. Okay? If it is freely falling, it will accelerate at 9.8 meters per second squared. So any object that we drop on Earth, if you drop this object, if you drop a rock off a bridge, it is going to speed up. The negative simply means in the downward direction. It's going to speed up at 9.8 meters per second each second. It's going to get faster in the downward direction, 9.8 meters per second faster each second. Okay? So on each planet has its own value of acceleration. Earth is what we're going to be focused on. So and on Earth, objects speed up 9.8 meters per second of speed change each second in the downward direction. The negative sign simply indicates downward direction. Okay, so for example, if in the absence of air resistance, if we drop a hammer and a feather, they will, after 1 second, they will have fallen a certain distance, and they would be at their speed at the 1 second mark. They're continuously getting faster and faster and faster. But at 1 second, their speed would have changed to 9.8 meters per second downward speed. After 2 seconds, another 9.8 meters per second of downward speed. So now they'd be at 19.6 meters per second of downward speed. And after 3 seconds, 29.4 meters per second of downward speed. And these objects are kind of presented as being spaced out more because in the first second, since they're going relatively slow compared to how they would be later on, the distance that the object falls is relatively small in the first second, more in the second second, and more in the third second because the objects are getting faster and faster. This would be true if we were in a vacuum. If air was not, if we drop this, and I'm actually going to show you a video where we actually do drop a feather and a bowling ball in a vacuum, and you will see that the two objects actually do speed up towards the Earth at exactly the same rate. But in the presence of air, the feather, because it's slamming into a lot of molecules in the air, right? The air right in front of us has oxygen and nitrogen and carbon dioxide and molecules. As the feather, because it's so light and has such a large surface area, as it hits the air, it will not continuously get faster and faster and faster at 9.8 meters per second. But a hammer will. So if you drop a hammer, it's going to speed up at 9.8 meters per second squared. If you drop a pen, most objects are going to speed up at 9.8 meters per second squared. A feather, however, it'll speed up, but after it gets a pretty modest amount of speed, and it's hitting enough air molecules, it will stop speeding up at 9.8 meters per second squared. So an object has to be in free fall to say that it is accelerating at 9.8 meters per second each second. But most objects, baseballs, hammers, a set of car keys, a book, almost a person who jumps out of a second store window, anything like that is going to be accelerating at 9.8 meters per second of speed change each second in the downward direction. Okay, so acceleration 9.8 meters per second each second in the downward direction. Okay, so how do we solve problems involving freely falling objects, let's say dropped objects? Well, we have our 4 motion equations. This is just distance equals average velocity. So initial velocity plus final velocity divided by 2, that's average velocity times time. This equation is basically acceleration equals change in velocity divided by time. Just solve for velocity final. So velocity final equals velocity initial plus acceleration times time. These are our 2 basic equations, right? This is just displacement equals average velocity times time. And this equation is acceleration equals change in velocity over time. Right? That's what both of these are basic equations. These are 2 derived equations where that are also useful for solving problems. This equation does not have velocity final. This equation does not have time. This equation here does not have distance, and this equation does not have acceleration. So it says we can use our 4 kinematics equations to solve dropped object problems. Now, when a very common problem involving free fall is dropping an object. So for any dropped object, when you drop an object, we're saying the initial velocity will be 0. We're assuming you drop it out of, let's say, your hand. And so while it's resting in your hand, its initial speed is 0. As soon as you let it go, it's going to start speeding up in the downward direction. And acceleration due to gravity is going to be 9.8 meters per second of speed change each second in the downward direction. Okay? If an object is traveled, it's only going to be traveling in the downward direction. And therefore, it's easiest to consider down as positive. So when you're solving these problems, we can consider down to be positive, or we can consider up to be positive and down to be negative. Right? So we can, if we want, choose either configuration. When you're talking about dropped objects, when you say an object is dropped, it's easiest to consider down as positive. Okay, and what does that mean for us? That means if we drop an object, as it moves more and more and more in the downward direction, we're assuming it's moving in the positive direction for displacement. As the velocity speeds up, in the downward direction, we're assuming the velocity becomes more and more positive. And so our distance displacement, it becomes more and more positive. Our velocity becomes more and more positive. And our acceleration is simply positive at 9.8 meters per second of speed change each second. So all of our variables are positive. That's why it's easier when we're working on problems involving dropped objects to consider down as positive. Okay? When we're talking about objects that are thrown up in the air and then come back down, it's usually easier to consider up as positive. When we consider up as positive, then as it moves, as the object, let's say we throw a baseball upward, as it's moving up and up and up, its displacement would be going more and more positive. On the way down, its displacement would be getting closer and closer to zero. The velocity would be positive on the way up, the velocity would be negative on the way down, and acceleration, since acceleration is always pointing downward toward like the Earth, acceleration will be negative. But when we've dropped objects, everything is positive if we consider down to be positive. That's why for this case it is easier to consider down to be positive. Okay, so let's just do an example. A rock is dropped off of a 25-meter tall cliff. How fast will it be moving when it reaches the ground? How fast? So we're interested in final velocity. Dropped means initial velocity is zero. Okay, so dropped object, we know our initial velocity is zero. It didn't say acceleration is 9.8 meters per second squared, but because the problem described it's kind of understood you're on planet Earth, the acceleration is known to be 9.8. So it's not going to specifically say in the problem acceleration on Earth is 9.8 meters per second squared. It's sort of understood that you know that, okay? And then our distance is 25 meters. And what is our unknown? Final velocity. Okay, so our given information is initial velocity is 0, acceleration 9.8, distance or displacement is 25 meters. Our final velocity is what we're trying to figure out. Okay, so we look at our four equations. Let's just go back here. So what don't we have here? We don't have time anywhere in this equation, right? We're not given time. We're not asked to find time. And if we look at our four equations here, well, which one doesn't have time in it? The first equation has time, the second equation has time, the third equation has time. This equation does not have time, so that's why we're choosing that equation. Okay, so we choose this equation. Velocity final squared equals velocity initial squared plus 2AD. And then we just plug in what we know. Final velocity is what we're looking for. Initial velocity is 0. 2. A, acceleration is 9.8. D, distance, 25 meters. Okay, we're considering down to be positive in this case, so we're making the acceleration positive 9.8. We're making the distance positive 25 meters, and our velocity in the end is going to be a positive velocity. All right, and then we just multiply these two numbers. 25 times 2 is 50. 50 times 9.8 is pretty close to 500. And we take the square root of that, and we're going to get our answer, 22 meters per second. So right before this rock hits the ground, the final velocity is 22 meters per second. Okay? All right. Now, what if we have the other kind of problem, which is an object that's thrown, this is thrown downward, okay? So if we have an object that is thrown downward, its initial velocity will not be 0. So you simply plug in the initial speed. The initial speed would not be 0, okay? Now, if it's thrown downward, again, we only have downward motion, and so we would, in this case, we would say, let's consider downward to be positive, right? If we're at the top of a cliff and we throw an object down, and when it leaves our hand, it's traveling downward at 5 meters per second, and then it speeds up on its way all the way down to the ground. Again, it's easiest to consider down to be positive in this case. That way all the variables stay positive. Okay? So here's an example of a downward motion problem. college student reaches out his window and throws a water balloon straight down toward another student standing on the sidewalk. If the balloon was thrown downward at 2 meters per second, so that's the initial velocity now. Our initial velocity is 2 meters per second. And it's going to fall a distance of 5 meters before hitting the student. So that's our distance that it's going to travel. Acceleration isn't explicitly stated, but we know it is 9.8 meters per second squared in the downward direction. Okay. And the question is how long, which is time, how long will it be before the student ends up getting hit? Okay, so again, we have velocity initial, acceleration, the distance, the time. What do we not see in this equation? In any of these four variables, we don't see final velocity. So we would look at our four equations and we'd say, which equation doesn't have final velocity? This one does, this one does, this one does not, this one does. So this is a good choice of equation to solve this problem. All right, so distance equals velocity initial times time plus 1/2 at squared. So we'll come back here and we say distance equals velocity initial times time plus 1/2 at squared. We plug in our distance, is 5 meters. Our initial velocity is 2 times time plus 1/2 at squared. All right. In this case, this is a somewhat tricky equation to solve. You'd have to use the quadratic formula, right? Negative b plus or minus square root, right? Negative b plus or minus radical b squared minus 4ac over 2a. Okay, so, and then you could solve this equation. You're not going to see anything that involves requiring the quadratic equation to solve on the Regents exam. And I will not give you anything like this on the tests either, but it is a method for solving these types of problems. Okay, next type of problem, throwing objects upward. Okay, object thrown upward. So now if you throw an object up, well now you've got motion going up and motion coming down. In this case, it's more practical to consider up as positive and down as negative. Okay, so in this case, when you have objects that are going up into the air, you want to consider up to be positive and down to be negative. Okay, objects that are thrown upward start with some positive initial velocity and slow to zero velocity at the highest point. So when an object is thrown upward at the highest point, it's given up all its upward speed. It has not yet begun to fall down yet. At that highest point, it's got zero velocity. Okay, and then it will have negative velocity on the way back down. The acceleration, since up is positive and acceleration acts downward, acceleration is negative 9.8 meters per second squared in this case. Okay. Displacement is positive on the way. Displacement, if you consider the ground to be zero, displacement would be positive, getting more and more positive as the object goes up, and then would becoming less and less positive on the way down. But displacement, generally speaking, will be positive because generally speaking, the ball is going up and down and staying at or above ground level the whole time. So displacement, generally speaking, is going to be positive. Okay. All right. Let's do an example. Okay. Well, actually, yeah, this is just an important graphic. Okay. So let's say we throw an object up into the air. What's going to happen is, let's say we throw it up with an initial velocity of 39.2 meters per second, which is pretty close to 40. And as an object accelerates, so it accelerates at 9.8 meters per second squared. And this number is pretty close as an approximation. It's pretty close to 10 meters of speed change each second, 10 meters per second of speed change each second, right? So just looking kind of roughly at the numbers, what you have here approximately is 40, 30, 20, 10, 0. Again, it's not exact, but it's approximate. So you can think of acceleration when you're kind of doing estimation. You can think of acceleration as it changes the speed of an object by about 10 meters per second of speed change each second, right? So this is pretty close to 40, pretty close to 30, pretty close to 20, pretty close to 10, 0. Okay, now it's not, acceleration is not exactly 10 meters per second of speed change each second. It's 9.8 meters of speed change each second. So 39.2, after 1 second, the object has slowed down 9.8 meters per second. So this number here is 9.8 less than this number. Now we're at 29.4 meters per second. A second later, our speed has been reduced by another 9.8 meters per second. A second later, our speed has been reduced by another 9.8 meters per second. And a second later, our speed has become 0. So it took 1, 2, 3, 4 seconds to give up all that initial upward velocity. Up here at the highest point now, our velocity has become 0. It has stopped going up. On the way down, we have a symmetrical process. At second 5, we're beginning to come right back down, and again, speed change continues to be 9.8 meters per second of speed change each second. But now we're starting at 0, and 1 second later, we're at negative 9.8 meters per second of speed change, which is symmetrical or the same as what you saw here, right? Except this was 9.8 meters per second going up. This is now 9.8 meters per second going down. A second later, our speed has increased to 19.6 meters per second in the negative direction. A second later, another 9.8 meters per second of speed in the downward direction. And a second later, another 9.8 meters per second in the downward direction. So what happens in the upward direction is kind of mirrored in what happens in the downward direction. We gave up 9.8 meters per second of speed. We gave up 9.8. We gave up 9.8. We hit 0. Took us 4 seconds to give up all that speed, and then it takes 4 seconds on the way down to build up all that exact same speed again. After 1 second, we're at 9.8, 19.6, and so forth. So if you throw a ball up, if you could throw a ball, or maybe shoot a ball up, where it would take 4 seconds to go all the way up in the air, well, it's going to take 4 more seconds to come all the way down, and when it comes down, it's going to have the exact same velocity that it had that you launched it upward with. It's a downward velocity now instead of an upward velocity. So whatever you shoot an object up with, it's going to come down, it's going to hit the ground with the same speed, or it's going to reach the height that you launched it from with the same speed that you launched it, just in the downward direction. Okay? And if it takes 4 seconds to reach its highest point, it's going to take 4 more seconds to come down and reach the ground again. Okay, so time up equals time down. That's an important relationship. Time up equals time down. And total time in the air is time up plus time down. Okay? So you definitely need to see that. Okay. Okay, so an object thrown up practice problem. Right. A baseball player hits a pop fly straight up in the air with a initial velocity of 10 meters per second. So you should be thinking, well, I know gravity slows down objects by about 10 meters per second each second, so you should be thinking when you see that, it's going to take about 1 second before it reaches its maximum height, before it gives up all that initial velocity, right? It's going to take 1 second to give up all this speed, and then it'll take another second to come back down to the ground. It's not going to be exact because acceleration isn't 10 meters per second squared, it's 9.8, but it's going to be pretty close to a second going up and a second coming back down again. Okay? How high will the ball travel into the air, and how long will the ball be in the air? Okay, well, what did they give us? They gave us an initial velocity of 10. Again, in this case, we're considering up. Anything that's up is positive. Anything that's down is negative. And since acceleration is down, acceleration is going to be negative 9.8 meters. Oops. Sorry. Negative 9.8 meters per second. Meters per second squared. All right. So velocity is upward, so it's positive 10 meters per second. Acceleration is acting downward, so it's negative 9.8 meters per second squared. Our final velocity, now we're not considering this to be the round trip because we're saying the final velocity is 0 at the highest point. So we're doing this analysis to the highest point, okay? And our final velocity will be negative 10 meters per second when it returns to the ground. Okay, so depends how we want to do our analysis. We could do our analysis to the highest point, or we could do our analysis to when the ball returns to the ground. Okay, so it's asking us though, how high will the ball travel? Well, that is the highest point. So let's look at, we want to know our distance to the highest point, okay? And then we also want to know time total. So let's figure out our distance to the highest point. So which equation has initial velocity, acceleration, final velocity, and distance, but does not have time? Well, velocity final squared equals velocity initial squared plus 2AD does. So let's use that equation. Our initial velocity is 0. Our final velocity is 0. Our initial velocity is 10. Now this is our final velocity at the highest point. So this analysis is to the highest point. And at the highest point, our final velocity is going to be 0. Okay, so 0 at the highest point. Initial velocity is 10 meters per second. 2a is operating downward, so it's negative 9.8 meters per second squared times d. So we plugged in all the numbers. The only thing that we have yet to solve for is distance or displacement. So we just do the math, right? 2 times 9.8, 10 times 10. This would basically be 0 equals 100 minus 19.6 d, right? And we simply solve this. We could add 19.6 d to both sides. We'd end up with 19.6 d equals 100. Divide both sides by 19.6, and we're going to get d equals 5.1 meters. Okay, so it's just doing the algebra. Okay, so we solve for distance. So we're done. We answered the first question. How high will the ball travel into the air? It'll travel 5.1 meters. Second question, how long will it be in the air? Okay. So the easiest way to do that is to say final velocity equals initial velocity plus acceleration times time. All right, so what's our final velocity? Now, there's two ways you could do this. You could say my final velocity at the highest point is 0, and you could plug that in, and you would be computing the time to the highest point, and then at the end you would simply double that time. Or you could say, well, I know my final velocity, since the ball went up at positive 10 meters, left the ground at positive 10 meters per second, it's going to come back to the ground at negative 10 meters per second, and I could plug that in as my final velocity, and then this would be my up and downward trip. This would compute my total time of the ball being in the air. So let's do that. So we're plugging in a final velocity of negative 10. That's when the ball comes back down to the ground. Our initial velocity is positive 10. Acceleration is negative 9.8 because we're using down as negative. And we're going to compute time, okay? So what would we do? We'd subtract 10 from both sides. You'd have negative 20 equals negative 9.8t. The negatives are going to cancel. 20 divided by 9.8 is going to be a little bit more than 2. They're kind of rounding this a little bit. And so time works out to be about 2 seconds. Okay, so again, we're using our 4 equations. Distance equals average velocity times time. Acceleration, this is basically acceleration equals change in velocity divided by time. Velocity final squared equals velocity initial squared plus 2AD, and distance equals velocity initial times time plus 1/2 AT squared. We're using those 4 equations to solve problems with projectile motion. All right, so let's do a positive physics problem. All right. Oops. Got to get this. There we go. Now we can see it. Okay. Okay, here we go. A student fires a cannonball vertically upward with a speed of 32 meters per second. Okay, so that's our initial velocity is positive 32 meters per second. We're considering up to be positive. Okay, up is positive. Down is negative. Determine all unknowns and answer the following questions. Neglect drag, that just means neglect air resistance, or it lets us assume it's perfectly projectile motion, or free fall rather. Neglect initial height, neglect horizontal motion of the cannonball. So we're assuming the cannonball really goes straight up and straight down. Okay, so we want to know how long did the cannonball rise? That's how many seconds. That's basically time up. It's going to be how much? And you could kind of estimate this. As I said, gravity changes the speed by about 10 meters per second each second. So after 1 second, this is going to be about 22 meters per second of speed. Another second later, it'll only be 12 meters of speed. Another second later, it'll be 2 meters per second of speed. So basically, this is going to take about 3.2 seconds going up. And it'll take another 3.2 seconds going down. And you should have a sense of that by just saying, hey, I know gravity is going to reduce the speed in the upward direction by about 10 meters per second each second. So, just you should know and intuitively get that time up is going to be about, not exactly about, I'm trying to draw a squiggly line, about 3.2 seconds. And time down is therefore also going to be about 3.2 seconds. And so our total time of flight is going to be about 6.4 seconds. So it's easy to figure that out by understanding that that gravity changes the speed of objects by about 10 meters per second each second in the downward direction. But let's compute this. Let's compute these. And then we'll figure out maximum height later. So which equation should we use? We know initial velocity. We know what we're looking for is time. Okay, we want to know, let's say, time to the highest point. We know at the highest point, our final velocity is going to be 0. We know when the object comes down again, the final velocity is going to be negative 32 meters per second. But since we're looking for how long did it rise, well, at the highest point, its final velocity is going to be 0. So we know this. We want to find this. We know one other thing that wasn't specifically called out in the problem. We know that the acceleration due to gravity is negative 9.8 meters per second squared. Okay, we know that gravity changes the speed of objects by 9.8 meters per second each second in the downward direction. Okay, so which equation involves all of this? The best equation is velocity final equals velocity initial plus acceleration times time. Okay, if our final velocity is 0, our initial velocity is 32 meters per second. Acceleration is negative 9.8 meters per second squared times time. Okay, now we'll simply we'll simply add 9.8t to both sides. We're going to drop the units. 9.8t equals 32. Divide both sides by 9.8. And again, you can see that this is going to be pretty close to 3.2 seconds, like we said in the beginning. But if we want to actually calculate it, I'm going to pause for 1 second. All right, I used my calculator and I computed 3.27 seconds. So we did the 32 meters per second divided by 9.8 meters per second squared, 3.27 seconds. So how long did it take the cannonball to rise? 3.27, and the units are seconds. So what's the total time of flight? Well, it's 3.27 seconds going up and 3.27 seconds going down. This is going to be 6.54 seconds. So what's our total time of flight? 6.54 seconds. All right, so we got that. Oops. Draw a little line. All right, so now we have Good. All right, so now we want to do the last thing. What was the actual height of the cannonball at the top? Well, what are we trying to find? D. We're trying to find displacement or distance at the top. All right, well, we can do a couple things. We can use, now that we have time, we can really use any equation that we wanted, that we want to. If we, but we could do, so we could do distance is average velocity times time, right? We know our initial velocity is 32, our final velocity is 0, so we could say our average velocity is 16 meters per second times 3.27 seconds going up, and we could get our answer that way. We could use distance equals velocity initial times time plus 1/2 AT squared, and we can plug in our initial velocity 32, time is 3.27 seconds to the highest point, plus 1/2, acceleration is negative in this case because up is positive, negative 9.8, and for t, plug in 3.27 seconds again, and we would get distance this way. And we could also do velocity final squared equals velocity initial squared plus 2AD. And we could plug everything in here and get distance this way as well. So I'm going to use this way only because, well, let's just say if we had made a computational error here and our time was off and we used one of these formulas, then this answer would also be incorrect. So just to be conservative, I'm going to use this formula, which doesn't rely on our computed answer. It relies on the information that was given in the problem. Okay? So here, velocity final at the highest point, right? We're trying to find the maximum height. So at the highest point, our final velocity is 0 meters per second. Our initial velocity was 32 meters per second, and that's going to get squared. Plus 2, acceleration is negative 9.8 meters per second squared, right? Up is positive, down is negative, times d, right? So we basically take 32 squared, and this is going to be 2 times 9.8 is negative 9.6. So what we have here is, and if we add 19.6 to both sides, we'd have 19.6d equals 32 squared. So d would be 32 squared divided by 19.6, and you compute that, and that is something worthy of a calculator. And I'm back from my calculator, and my calculator came out to 52.25. Okay, so my total distance going upward was 52.25 meters. Okay, which looks about right from this perspective as well. 3 times 16 would be 48, so a little bit more than 48. That sounds about right. So 52.25 meters looks about right. And 52.25 meters. Okay, so that's how we solve the problem. Again, we're using, as you're noticing, we're using these kinematic equations all the time. We're using these 4 equations all the time. You do have to be sensitive to, is up positive or is down positive, and adjust the sign of the acceleration appropriately. Right? Let's just do another one. Okay, a student fires a cannonball vertically upward. The cannonball returns to ground after 2.9 seconds of flight. So that's time in the air is 2.9 seconds. Determine all unknowns, neglect drag, etc., etc. Use regular units, meters. Okay, so this is really all they've given us. And but what do we know? We know if the total time in the air was 2.9 seconds, and we know the time going up is half of that, which is 1.45 seconds, and we know the time coming back down would be 1.45 seconds. We know acceleration is negative 9.8 meters per second squared. And we want to know, and we want to know at the highest point, we know way up here at the highest point, our final velocity is going to be 0. All right, so we should be able to answer some of these questions. Let's start with this one. How long did the cannonball rise? Well, we already got that. It's half of the total time in the air is the time going up. So how long did the cannonball rise? 1.45 seconds. Okay. What was the cannonball's initial speed? Well, so we're trying to find VI. We know acceleration. We know time. So what would a good equation be? Well, we could say a good equation could be, oops, sorry about that. An appropriate equation would be velocity final equals velocity initial plus acceleration times time, right? This is basically acceleration equals the change in velocity divided by time. Well, we know at the tip top, our final velocity is 0. Our initial velocity is what we're trying to find. Acceleration is plus, make this a plus. Acceleration is negative 9.8 meters per second squared. And time going up is 1.45 seconds, okay? So whatever this product is, if we add it to both sides, we'd have 9.8 times 1.45 equals velocity initial. And then we plug that into our calculator, and we get, which should be, it's a little bit less than 1.5 times 10, so it should be a little less than 15. Let's see what it is, which is 14.21 meters per second is our velocity initial. I just used a calculator to do that. Okay, so what was the cannonball's initial speed? 14.21 meters per second. Okay, and then what was the cannonball's maximum height? Well, that's d, right? That's distance or displacement. And so we could do distance equals velocity initial times time plus 1/2 AT squared. We could do this. But the easiest way to actually do this, as I said, you could think the distance it's going to travel through, you could think of it, it's got an initial velocity of 14.21 meters per second and goes up to 0. But it's the exact same process on the way down, where it starts with 0 and it falls down to the ground and ends up with 14.21 meters per second of speed. So I'm going to think of this as it started up here and it fell down to the ground. I'm not going to think of it as what distance did it take to go up. I'm thinking of it as what distance did it take as it was falling down, right? And if I think of it that way, I can set my initial velocity to 0. The advantage of that is it makes this term disappear, and I get 1/2 a 9.8 meters per second squared, or negative, I could say negative, times time squared. Time is 1.45 seconds to make the either the journey up or the journey down squared. Okay, I multiply this times this times this, and the sign's going to be negative because that's how far did it fall downward from its highest point. But I know that is the distance it fell through, so I could just consider that to be positive and plug it over here. So let me just do that for one day, which works out to be 10.3 meters. Okay, so I'll leave it here since we're already at quite a long video. But I just wanted to show you that, again, to solve these free fall problems, we're really going to be using our 4 kinematics equations. Velocity final equals velocity initial plus acceleration times time. Distance equals velocity initial times time plus 1/2 AT squared, and the other 2 equations. So you're going to be using all 4 of those equations. Which equation you pick, just use that graphs method that I spoke about. Identify the given information, identify the required information. That will lead you to pick the appropriate equation out of the 4, plug the numbers into the equation, and solve it. You'll get your answers every single time. Okay? All right, thank you.